In the vast expanse of the cosmos, beyond our own sun-soaked solar system, lies a treasure trove of worlds just waiting to be explored. Imagine staring up into the night sky, filled with countless stars, and realizing that many of those twinkling points of light shine upon planets that orbit them, each one a unique realm of its own. This burgeoning field of exoplanet discovery, the search for planets beyond our solar system, has ignited a cosmic quest unlike any other. As we peel back the layers of our universe, researchers have confirmed thousands of these distant planets, revealing a multitude of environments that challenge our traditional understanding of how planets form and evolve. Each new discovery sparks excitement and wonder, as scientists detect planets with conditions so unlike Earth's, yet intriguingly familiar. These worlds can be gas giants, icy realms, or rocky shores, showcasing the incredible diversity the cosmos has to offer. The significance of exoplanets extends far beyond a mere tally of new worlds. Each planet holds the potential to unlock secrets about the very nature of our universe. Not only do they help us understand the formation of planetary systems, but they also offer insights into the potential for life beyond our own. Picture a planet orbiting a distant star, cloaked in a hazy atmosphere that hints at complex chemical processes. Could it harbor life? It's questions like these that drive scientists to study the atmospheres of these newfound worlds. The technological advancements that make the search for exoplanets possible are as captivating as the planets themselves. Instruments like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS, have revolutionized our ability to detect these distant bodies through methods such as the transit technique. By observing the slight dimming of a star's light as a planet passes in front of it, we can infer the planet's size and orbit. Each data point collected brings us one step closer to unveiling the mysteries these atmospheres conceal. Among the most exciting realms of exoplanet research is the investigation of their atmospheres. Just like our own Earth, exoplanets can possess thick gases, thin clouds, or even volatile storms. Scientists are utilizing advanced spectroscopic techniques to analyze the light filtered through these distant atmospheres. By measuring how different wavelengths of light interact with various gases, we can gain insights into the chemical compositions of these alien worlds. The early discoveries of exoplanets raise the tantalizing possibilities of what we might find in their atmospheres. Early studies focused mostly on gas giants located close to their stars, known as hot Jupiters. These massive planets, often reminiscent of our own Jupiter but transcending it in size and temperature, are prime candidates for atmospheric analysis. Imagine glowing, high-pressure atmospheres swirling with clouds of metal and vapor. The data coming back from these observations can shock us, revealing unexpected compounds and conditions. Emerging technologies and missions, such as the James Webb Space Telescope, are poised to advance our knowledge further still. Its cutting-edge equipment will allow astronomers to explore exoplanet atmospheres with unprecedented detail. They will search for the presence of essential elements like water vapor, methane, and carbon dioxide, forming crucial clues about habitability. Each piece of data serves as a breadcrumb that may lead us toward finding life. In framing our search for other worlds, the diversity of exoplanets offers a stark reminder of our own planet's unique circumstances. Earth enjoys a delicate balance. Its atmosphere, enriched with oxygen, maintains a temperature regulated by the greenhouse effects. However, other planets may display extreme conditions, with thick layers of greenhouse gases that trap heat to create blistering environments or frigid surfaces where life as we know it could not endure. As we turn on our telescopes toward the night sky, we become explorers in the vast ocean of stars, each shining point harboring worlds of possibility. The journey reveals not only the diversity of solar systems, but also reflections of our own origins and the dynamics of planetary evolution. We stand at a pivotal moment, armed with new knowledge and advanced searching tools, each discovery bringing us closer to understanding the foundational questions. Where did we come from? Are we alone in the universe? In the exploration of exoplanet atmospheres, we are not just gathering data. We are weaving a narrative that spans across light years and epochs. As we continue this cosmic quest, the beauty of the universe unveils itself, nurturing our curiosity and fueling our dreams of discovering what lies beyond the veil of our own solar system. With every new planet observed, we find ourselves asking not just about their chemical makeup, but about the very essence of existence within an endless sea of stars. Exoplanets, or extrasolar planets, are celestial bodies that orbit stars outside our solar system. The term encompasses a wide variety of worlds, each unique in its own right, presenting a diverse tapestry of environments. To date, astronomers have confirmed the existence of thousands of exoplanets, revealing an astonishing array of sizes, compositions, and climatic conditions. Imagine peering into a cosmic sea, where some planets are mere whispers of gas, while others are rocky giants, akin to Earth but distant in both space and experience. The classification of exoplanets is primarily based on their characteristics and distances from their host stars. Scientists often categorize them into several groups: terrestrial planets, which are rocky and Earth-like; gas giants, massive planets composed mainly of hydrogen and helium; ice giants, which have thick atmospheres shrouding their icy core. There are also subcategories such as super-Earth planets larger than Earth but smaller than Neptune that can have their own unique atmospheres and surface conditions. This classification system helps researchers not only to understand the planets themselves, but also to draw comparisons with our own planetary system. To discover these distant worlds, astronomers employ various innovative methods, with the two most prominent techniques being the transit method and the radial velocity method. The transit method, perhaps the most celebrated of these, involves detecting a temporary dimming of a star's light as a planet passes in front of it. This brief occlusion provides a wealth of information, such as the planet's size and orbital period. Each transit can create a pattern within the light curve of a star, allowing astronomers to infer the presence of an exoplanet. It's a delicate dance, almost a cosmic heartbeat, where the rhythm of light and shadow reveals the universe's secrets. On the other hand, the radial velocity method, also known as the Doppler method, focuses on the gravitational tug that a planet exerts on its parent star. As the planet orbits, it causes the star to wobble slightly. This wobble can be detected through shifts in the star's spectral lines, revealing crucial details about the planet's mass and the shape of its orbit. These subtle movements offer yet another lens through which to view the dynamics of celestial bodies in distant solar systems. Beyond these techniques, an ever-expanding array of discovery tools continues to emerge. Missions equipped with advanced photometers and spectrometers, such as the Kepler Space Telescope and the more recent James Webb Space Telescope, allow us to peer deeper into the cosmos. These instruments open a window to analyze exoplanet atmospheres, searching for particular elements or compounds that could hint at habitability. By identifying signs of water vapor or other life-sustaining substances, we inch closer to answering one of humanity's most profound questions. Are we alone in the universe? As we delve into the atmospheres of exoplanets, we must also recognize the importance of understanding their environments. For instance, some planets orbit so closely to their stars that they experience extreme heat, leading to scorching temperatures and hostile conditions, while others circle at a distance that might allow for liquid water to exist, a vital ingredient for life as we know it. This variation is essential for piecing together the complex puzzle of planetary formation and evolution. Considering the context of these discoveries, we reflect on the scale of our universe. The Milky Way alone is home to billions of stars, many of which likely host their own planetary system. With each new exoplanet we find, we accumulate not just data, but a deeper understanding of our place in this immense cosmos. As scientists continue to refine their techniques and deepen their analyses, the potential to unlock more secrets of distant worlds is both exciting and humbling. Imagination and curiosity are our guiding stars as we pursue the mysteries of these alien worlds, forever expanding our understanding of what lies beyond the boundaries of our own solar system. In the realm of exoplanets, we are not merely passive observers, but active participants in a quest that straddles the line between science and wonder. Each discovery adds a thread to the rich tapestry of knowledge, inviting us to dream of what might be beyond our sight. With each revelation, the universe becomes a little less unknown, a little more familiar, and endlessly fascinating. As we embark on our exploration of exoplanets, one vital aspect captures our attention: their atmospheres. The study of these distant worlds does not end with their discovery. Indeed, it is the atmospheres that offer a closer glimpse into their potential for habitability. Understanding an exoplanet's atmosphere is essential, as it acts like the protective shell surrounding the planet, shaping its environment and influencing the possibilities for life. Imagine standing on an alien world, looking up at a sky painted with different colors. The atmosphere determines not only what you see, but also the conditions you would experience. The temperatures, the weather patterns, and even the presence of essential gases. Much like Earth, an exoplanet's atmosphere can reveal a great deal about its surface conditions, energy balance, and processes that may support life. One of the primary reasons we focus on these atmospheres is their relationship with temperature. The composition of an atmosphere plays a critical role in trapping heat, a phenomenon known as the greenhouse effect. Our own planet benefits from a balance of greenhouse gases, which helps maintain a stable temperature that is conducive to life. However, if certain gases dominate an atmosphere, they could unleash a runaway greenhouse effect, leading to extremes in temperature that would render a planet uninhabitable. By analyzing the gases present in an exoplanet's atmosphere, scientists can infer whether it is in a state that allows for liquid water, a fundamental requirement for life as we know it. Moreover, atmospheric compositions hint at various geological and biological processes. For example, the presence of oxygen might suggest biological activity, since this gas is primarily produced by photosynthetic organisms. If we detect oxygen along with other gases like methane, it may imply that some form of biological processes are occurring, as these two gases tend to interact and would rarely coexist in significant quantities without ongoing production. This tantalizing hint could bring us a step closer to answering one of humanity's most profound questions. Are we alone in the universe? We also delve into the complexities of climate patterns in different atmospheres. Some exoplanets exhibit rapid changes in temperature, intense storms, or extremely thick clouds, unlike any weather systems we experience here. The study of these phenomena enhances our understanding of atmospheric dynamics, ultimately offering insights into how such variations can affect potential habitability. By observing the weather patterns of distant worlds, we can gain knowledge applicable to Earth's own climate system, enhancing our capacity to address pressing environmental issues on our home planet. Furthermore, research into exoplanet atmospheres sheds light on their potential for retaining essential elements. For instance, gas giants possess vast atmospheres that can offer clues to their formation and development, while terrestrial planets with thinner atmospheres provide insights into their evolution and capability to maintain basic life-supporting conditions. Each planetary type brings invaluable data, helping scientists draw comparisons that deepen our understanding of planetary diversity. The advanced technology we wield today enables us to probe the atmospheres of these mysterious worlds with unprecedented detail. Telescopes, like the James Webb Space Telescope, will actively analyze light passing through exoplanetary atmospheres, identifying specific wavelengths corresponding to various molecules. Each molecular signature tells a story, providing clues about temperature, pressure, and chemical reactions occurring within these distant skies. This process is akin to reading a book written in a language not yet understood, where every word can hint at a larger narrative. As we broaden our scope to exoplanets situated in their stars' habitable zones, regions where conditions are just right for life, we find ourselves contemplating how unique our own planet is. Could there be worlds out there with conditions that mimic Earth, preserving the delicate balance that fosters life? By studying atmospheres, scientists can identify targets for further investigation, constantly refining our search for extraterrestrial life. Ultimately, the significance of exoplanet atmospheres lies in what they reveal about the possibility of life beyond Earth. With each new discovery, we are not merely cataloging these worlds. We are engaging in a profound quest for understanding our place in the vast cosmos. The atmospheres of exoplanets hold potential secrets that could redefine our knowledge of biology as we comprehend it. The search continues, illuminating pathways toward a greater understanding of existence, one breath of atmosphere at a time. Now, as we look deeper into these atmospheric mysteries, let us consider how they not only inform us about foreign worlds, but also bring profound insight into our own planet's future and sustainability. In this boundless universe, the search for life might just begin with a careful examination of the air that envelops these distant orbs. As we venture deeper into the realm of exoplanets, it becomes essential to understand how scientists are able to unlock the secrets of these distant worlds. The key to this exploration lies in the remarkable advancements in telescope technology and analytical instruments developed over the past few decades. One of the most notable achievements in this domain is the James Webb Space Telescope, or JWST, which serves as a powerful tool for observing exoplanet atmospheres in unprecedented detail. Launched in December 2021, the James Webb Space Telescope is not merely an upgrade from its predecessor, the Hubble Space Telescope. It is an entirely new chapter in our quest to understand the universe. Webb is distinguished by its 6.5-meter primary mirror, which is significantly larger than Hubble's, allowing it to collect more light and capture images with exceptional clarity. Its position at the second Lagrange point, about 1 million miles from Earth, places Webb in an ideal location to observe the cosmos without the interference of Earth's atmosphere. One of the most groundbreaking features of the James Webb Space Telescope is its ability to analyze the atmospheres of exoplanets. Through a method known as transmission spectroscopy, Webb detects the light that passes through an exoplanet's atmosphere as it transits in front of its host star. When the starlight filters through the planet's atmosphere, specific wavelengths of light are absorbed by the gases present, leaving behind a unique spectral fingerprint. By examining these fingerprints, scientists can determine the composition, structure, and even the weather systems of far-off worlds. But how does the data from Webb actually come together to provide these invaluable insights? When telescopes like Webb observe an exoplanet, they gather massive amounts of data, which researchers then analyze using sophisticated computer algorithms and models. These computational techniques help to distinguish the faint signals of an exoplanet's atmosphere from the overwhelming brightness of its parent star. This challenge is akin to listening for a whisper in the middle of a crowded room. But with the right tools, scientists can discern even the most subtle nuances of a planet's atmospheric components. Beyond Webb, other instruments also contribute to our understanding of exoplanet atmospheres. The Hubble Space Telescope, though operating for over 3 decades, still plays a vital role in atmospheric studies. It utilizes both imaging and spectroscopy techniques to investigate the atmospheres of numerous exoplanets, especially those orbiting very close to their stars. This combination of observations from both Hubble and Webb provides a comprehensive view of these worlds. Other ground-based observatories, such as the extremely large telescope currently under construction in Chile, are set to enhance our ability to study exoplanetary atmospheres. With mirrors up to 39 meters in diameter, these telescopes will be able to capture more light than ever before, offering new perspectives on even fainter planets. Using cutting-edge adaptive optics technology, they will compensate for the blurring effects of the Earth's atmosphere, delivering crisp and clear images that can rival those from space-based telescopes. In addition to advanced telescopes, powerful analysis techniques are crucial for interpreting the data collected by these instruments. Machine learning and artificial intelligence are beginning to play a transformative role in analyzing complex datasets. By leveraging algorithms trained on vast amounts of astronomical data, these tools help identify patterns that might be overlooked by human researchers. This interdisciplinary approach not only accelerates the pace of discovery, but also enhances our understanding of the diverse atmospheric conditions present across various exoplanets. Another remarkable technology involved in this research is the use of spectrographs. These instruments are essential for detailed observations as they break down light into its constituent colors, revealing the unique signatures of different atmospheric components. For example, the presence of water vapor, carbon dioxide, or methane can significantly inform scientists about the potential habitability of a planet. By combining data from various spectrographs on board different telescopes, researchers gain a more robust understanding of the atmospheric dynamics and chemical processes that may be occurring on these distant worlds. As we reflect on the technological advancements that are shaping our understanding of exoplanets, it is evident that we are witnessing a renaissance in astronomical research. The capability to analyze the atmospheres of these distant worlds not only widens our perspective of life and its potential forms across the cosmos, but also encourages us to look back at our own planet through a new lens. The secrets we uncover about exoplanets will enhance our understanding of planetary atmospheres in general, shedding light on the complex interplay between geology, climate, and the possibility of life. In this era of discovery, as we continue to unveil the atmospheres of distant exoplanets, we stand on the threshold of exciting revelations. With each new finding, our place in the universe becomes clearer, and the quest for knowledge about the billions of worlds that exist beyond our own feels more tangible than ever. Through this journey, not only do we learn about distant planets, but we also deepen our connection to the cosmos itself, illuminating the intricate web of existence that ties us all together. As we journey deeper into the cosmos, we encounter an astonishing realm filled with possibilities, the atmospheres of distant exoplanets. One of the most fascinating aspects of this exploration is the quest to detect specific molecules within these alien atmospheres. Among the most significant molecules that scientists are investigating are water vapor and carbon dioxide. Their presence can unlock numerous secrets about a planet's environment, shaping our understanding of habitability in ways we are only beginning to fathom. Water vapor, often considered the cornerstone of life as we know it, holds extraordinary importance in our search for potentially habitable worlds. But why is water so crucial? On Earth, water plays a vital role in maintaining our climate, regulating temperature, and supporting a myriad of ecosystems. Thus, detecting water vapor on an exoplanet can provide a tantalizing first clue about its potential to harbor life. Scientists use advanced techniques to identify water vapor signatures during transit events, moments when a planet passes in front of its host star. As this occurs, starlight filters through the planet's atmosphere, revealing the fingerprints of various molecules, including water. In the last few years, telescopes like the James Webb Space Telescope have captured data that reveal these spectral signatures with remarkable precision. For example, researchers observed the atmosphere of WASP 121b, a hot Jupiter-y exoplanet. In this extreme environment, water vapor was detected alongside other molecules, creating a vivid picture of its atmospheric chemistry. This not only emphasizes the planet's intense heat, but also suggests dynamic processes that could influence its weather patterns. Water is not the only molecule of interest to astronomers. Carbon dioxide, too, provides a wealth of information. While often associated with greenhouse effects on Earth, the presence of carbon dioxide in an exoplanet's atmosphere can indicate several environmental processes at play. For instance, in higher concentrations, carbon dioxide might suggest geological activity, volcanoes releasing gases, for example, which could be essential for sustaining a balanced atmosphere over time. The detection of carbon dioxide is often achieved through similar transit methods, allowing researchers to identify absorptions in the star's spectrum resulting from the molecule's unique wavelength. Moreover, the combination of both water vapor and carbon dioxide can offer deeper insights. In our own solar system, Earth maintains a stable climate partly due to the delicate balance of greenhouse gases. These gases allow sunlight to enter, but trap some of the heat, preventing our planet from becoming too frigid. If we observe a similar juxtaposition of water vapor and carbon dioxide on an exoplanet, it could signal a stable environment with the potential for life, assuming other conditions are also met. Transitioning from the significance of these molecules, we must also consider the role of other gases in shaping our understanding of exoplanet atmospheres. Methane, for example, adds another layer of complexity. This molecule can indicate biological processes under certain conditions, as we see on Earth. Yet it's also produced by geological processes. Thus, methane's presence could hint at various possibilities, raising questions about whether life could have a stake in that world, or if the planet's geology is solely responsible. As scientists refine their detection methods, we can expect an increasingly nuanced understanding of how atmospheric constituents interact with one another. The interplay of these molecules can tell us about temperature distributions, cloud formations, and even winds within the atmosphere. For instance, insights from the K2-18b exoplanet revealed intriguing elements of water clouds and hints of methane, all of which suggest that astrobiology may not be confined to just terrestrial conditions. The implications of discovering water vapor and carbon dioxide, alongside methane and other constituents, extend beyond just the search for life, as we understand. These findings also help us explore the vast spectrum of potential environments that novel forms of life could inhabit. The existence of extreme conditions on exoplanets, such as scorching temperatures or intense pressure, challenges our preconceived notions about where life could thrive. As we grasp the delicate balance required for habitability, the quest to detect these molecules serves as a stepping stone toward identifying truly Earth-like exoplanets far beyond our solar system. Each detection brings us closer to answering profound questions about our universe's potential for life. Every molecule unveils a secret about the planet's history, its climate, and perhaps even its ability to support life forms unlike anything on our homeworld. In this fascinating realm where science meets imagination, we find ourselves not only observing distant worlds, but also redefining our understanding of life's possibilities beyond our own. As we continue to explore and learn, we come to realize that every exoplanet holds a story waiting to be told, one molecule at a time. To truly grasp the wonders of exoplanet atmospheres, let's explore a few notable case studies that highlight the diversity and intrigue of these distant worlds. Each exoplanet offers a unique glimpse into the processes that shape planetary atmospheres and the potential for life as we know it. One such fascinating world is WASP 121b, a gas giant located approximately 850 light-years away in the constellation Pegasus. WASP 121b is classified as a hot Jupiter, a type of exoplanet that shares characteristics with both gas giants and the immense heat usually reserved for proximity to their stars. This planet orbits its parent star in a mere 1.3 days, resulting in temperatures soaring around 2,500 degrees Celsius or around 4,500 degrees Fahrenheit. Such extreme conditions lead to a blistering atmosphere primarily composed of hydrogen and helium. But what truly captivates scientists is the detection of heavy metals in its atmosphere, including iron and magnesium. These metallic elements are usually associated with much cooler environments, but on WASP 121b, they exist in gaseous forms due to the intense heat. This extraordinary phenomenon allows us to glimpse the atmospheric dynamics shaped by such severe conditions. The presence of these metals hints at processes like atmospheric evaporation, where high temperatures and radiation strip elements from the planet's surface or lower atmosphere and loft them into the upper atmosphere, creating a cosmic ballet of particles. Now, let's turn our attention to K218b, a captivating exoplanet located about 124 light-years away in the constellation Leotoiaitacot. I am trying to silence. I'll be angry. Unlike WASP 121b, K218b orbits within its star's habitable zone, where conditions may allow liquid water to exist on its surface. This rocky planet is roughly 2.5 times the size of Earth and has a mass that suggests it could maintain a thick atmosphere, potentially rich in water vapor. Recent studies using powerful telescopes, including the renowned Hubble Space Telescope, have revealed the presence of water in K218b's atmosphere. This discovery ignited tremendous excitement in the scientific community, as water vapor is a key ingredient in the recipe for life as we know it. Furthermore, researchers detected hints of methane and carbon dioxide, essential components associated with biological processes on Earth. The significance of these findings cannot be overstated. They invite us to ponder whether K218b may host some form of life, or at the very least, present the necessary conditions for such life to flourish. The study of its atmosphere, particularly the balance of these gases, can provide us with crucial information about any potential biological activity. Would K218b support microbial life? Or are we merely observing a planet rich in chemical possibilities, devoid of life? As we drift beyond individual case studies, it's essential to consider the broader implications these atmospheres pose. The study of exoplanet atmospheres can help refine our understanding of where to search for life beyond Earth. By characterizing planets based on their atmospheric makeup, we can prioritize targets in our continued exploration of the cosmos. Additionally, it's remarkable to think of how the analysis of exoplanet atmospheres mirrors the study of environmental conditions on Earth. The same molecules we investigate in distant atmospheres play critical roles in our planet's climate and ecosystems. For instance, understanding the balance of greenhouse gases on K218b may provide insights into climate change and atmospheric dynamics on Earth. The secrets that these atmospheres hold are like whispers from the universe, guiding us to reconsider our place within it. As we refine our observational technologies and expand our quest into space, each new discovery acts as a key, unlocking additional mysteries about the nature of planets beyond our solar system. Our journey through the realms of distant atmospheres teaches us not just about alien worlds, but also about the fragile existence of our own planet. The gases and conditions we analyze today are interconnected with Earth's own story. As we continue our quest for knowledge, we remind ourselves that the curiosity that drives us to explore the universe is the same fervor that compels us to understand our home. With every revelation, every detailed observation from telescopes across the globe, and in orbit, we come closer to answering the most profound questions of our existence. The discoveries of planets like WASP-121b and K218b do more than expand our catalog. They spark a dialogue about life and the diverse environments that may exist across the cosmos. What more lies out there, waiting for us to find? Only time and continued exploration will tell. As we embark on the captivating journey of uncovering the atmospheres of distant exoplanets, it's crucial to recognize the challenges that scientists face in this groundbreaking field of study. Although significant strides have been made in analyzing these atmospheres, the task remains complex and filled with obstacles. One of the primary challenges in atmospheric studies is the sheer distance separating us from these far-off worlds. Exoplanets are often located many light years away, making it difficult for telescopes to gather adequate data. For instance, some of the closest exoplanets are still over 4 light years distant. The faint light that reaches us is often obscured by the brightness of their host stars, complicating observations. Researchers must use advanced techniques to separate the light from an exoplanet's atmosphere from the overwhelming glare of its star. This necessitates the use of sophisticated instruments that can finely discern these subtle signals. Despite our best efforts, this inherent limitation means that the data we collect is often incomplete and suffers from low resolution. Moreover, the interpretation of the gathered data is fraught with hurdles. Atmospheric composition is inferred from the light that passes through the atmosphere as a planet transits in front of its star. This method, known as transmission spectroscopy, analyzes the wavelengths of light that are absorbed by molecules within the atmosphere. However, translating these readings into a comprehensive understanding of atmospheric conditions is akin to piecing together a puzzle with many missing pieces. The complexity of interactions between different gases, pressure variations, and temperature layers can create a confusing picture. This is particularly true for the atmospheres of gas giants, where clouds and storms can mask key signatures, leading to potential misinterpretations. Another challenge stems from the diversity of exoplanets themselves. Each planet comes with its own unique set of conditions. For example, scientists have discovered hot Jupiters, which are gas giants that orbit very close to their stars, exhibiting extreme temperatures that challenge our assumptions about atmospheric dynamics. Conversely, cooler, rocky exoplanets may display atmospheres that bear stark contrasts to those found in our own solar system. As researchers look for signs of habitability, they grapple with the varied environmental factors that influence atmospheric behavior. This variety can breed misconceptions, as one planet's atmosphere might not serve as a reliable model for another. Common misconceptions can arise from the implications of atmospheric studies. The tantalizing discovery of molecules such as water vapor or carbon dioxide often leads to overzealous claims about potential life. While the presence of these elements can indicate habitable conditions, it does not guarantee the existence of life. It's important to remember that life, as we understand it, is dependent on a delicate interplay of many factors beyond mere chemistry. The conditions on an exoplanet could be inhospitable despite having the right building blocks for life. Thus, there's a risk of conflating potential with certainty, leading to public misunderstandings about the significance of atmospheric findings. Furthermore, the field is constantly evolving, with new observational techniques and instruments emerging. Each advance brings fresh hope, but also amplifies our urgency to understand what is still unknown. For instance, while the James Webb Space Telescope has provided unprecedented insights into exoplanet atmospheres, researchers must also contend with the ever-growing complexities of their findings. With each layer of data that is added, interpretation becomes more nuanced, yet fraught with ambiguity. This integral aspect of scientific inquiry underscores the importance of maintaining a sense of caution and humility. In summary, While the study of exoplanet atmospheres is one of the most exhilarating frontiers in modern astronomy, it is also marked by significant challenges and misconceptions. As we strive to decode the secrets held within the atmospheres of these distant worlds, we must tread carefully and consider the limits of current knowledge. The data we collect is constantly evolving, reflecting the complexities of the cosmos. Each discovery can spark excitement, but it also invites us to reflect deeply on what we truly understand about the universe and the tantalizing possibility of life beyond our own Earth. With each bit of knowledge we gain, we come closer to understanding our place in the vast expanse of existence, embracing both the wonder and the mystery that this pursuit entails. As we look to the horizon of exoplanet research, a thrilling era of exploration awaits. With advancements in technology and the ambitious missions in development, our understanding of distant worlds and their atmospheres is about to deepen in ways we have only begun to imagine. The next decade promises to bring us closer to unlocking the secrets these celestial bodies hold, fueling not just scientific curiosity, but our fundamental understanding of life in the universe. One of the most anticipated missions on the horizon is NASA's upcoming flagship observatory, the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. This mission aims to survey a wide swath of the sky, identifying thousands of exoplanets through gravitational microlensing and direct imaging techniques. By leveraging its large field of view, Roman will help reveal planets that are difficult to detect, including those orbiting distant stars in the habitable zones. This could dramatically expand our catalog, providing a rich array of targets for atmospheric study. Complementing this effort is the European Space Agency's Ariel mission, scheduled for launch in 2029. Ariel aims to deliver unprecedented insights into the atmospheres of over 1,000 exoplanets, spanning a broad range of sizes and temperatures. Its unique combination of spectrographs will allow scientists to analyze the light emitted and absorbed by the chemicals in these atmospheres with remarkable precision. By defining the chemical compositions of exoplanetary atmospheres, Ariel will play a crucial role in understanding their formation, evolution, and potential habitability. This mission truly embodies the collaborative spirit of international space exploration. As we anticipate these missions, groundbreaking technological advancements are already reshaping our capabilities. Innovations in telescope design, like adaptive optics, enable astronomers to correct for atmospheric turbulence, thereby reducing distortion and enhancing clarity in images of distant planets. These improved observations empower scientists to detect even faint signals from exoplanet atmospheres, making it possible to identify chemical signatures of life-sustaining molecules. Additionally, machine learning is revolutionizing exoplanet research. By harnessing the power of artificial intelligence, researchers can sift through vast amounts of data more efficiently than ever before. Algorithms can identify patterns and anomalies in the light spectra collected from exoplanets, isolating signals that might indicate the presence of key atmospheric components. This synergy between human intuition and machine processing creates a powerful engine for discovery. Moreover, the collaboration between space missions and ground-based observatories enhances our observational capabilities. Projects like the Extremely Large Telescope, currently under construction in Chile, will offer unparalleled resolution and sensitivity. It will allow scientists to conduct detailed observations of exoplanet atmospheres, bringing us closer to finding markers of biological activity or biosignatures. The combined efforts of these diverse observational platforms promise to enrich our understanding and broaden the range of planets we can study. Yet, there remains an underlying journey of patience as we learn to interpret the data these missions will collect. The atmospheres of exoplanets are complex and varied, Each world brings its own enticing puzzle, each atmosphere woven with unique environmental conditions and histories. The intricate dance of molecules reacts to the conditions present on each planet, creating environments that might be vastly different from our own. As we strive to decode these cosmic texts, we will continuously refine our models and theories, ensuring that each new discovery sharpens our understanding rather than diminishes it. Looking further into the future, missions beyond our current horizon, like the proposed Habitable Worlds Observatory, may one day allow us not only to detect atmospheres, but also to analyze them in detail for potential signs of life. This ambitious vision underlines our collective yearning to answer one of humanity's oldest questions: are we alone in the cosmos? As we inch closer to answering this profound mystery, we equip ourselves with the tools and knowledge to expand the boundaries of our understanding. In essence, as we chart this dynamic trajectory forward, we are on the cusp of a new renaissance in exoplanet research. The next generation of telescopes, sophisticated analytical techniques, and collaborative missions promise not just to peel back the layers of enigmatic atmospheres, but to weave a richer tapestry of our universe. With each breakthrough, we are reminded that our quest for knowledge is as boundless as the cosmos itself. The secrets held within the atmospheres of exoplanets await us, ready to guide our journey deeper into the mysteries of existence. As we draw near the conclusion of our exploration into the atmospheres of distant exoplanets, it's essential to take a moment to reflect on the broader implications of our discoveries. Each time astronomers identify a new world, each time we unveil the secrets hidden within their gaseous envelopes, we are not simply cataloging distant celestial bodies. We are enriching our understanding of the universe, of life itself, and of our place within this magnificent expanse. Consider for a moment the sheer scale of this undertaking. As of now, thousands of exoplanets have been identified, each unique in its properties, its conditions, and its potential. Yet, what truly captivates our imagination is the realization that among these worlds, some may harbor atmospheres capable of supporting life. The possibility that we might not be alone, that other forms of life could exist on planets orbiting distant stars, challenges our perceptions and ignites our wonder. These discoveries encourage us to look beyond our own blue planet, prompting us to ask profound questions about existence, evolution, and the fundamental nature of life. The advent of cutting-edge technology, particularly the James Webb Space Telescope, has unlocked unprecedented capabilities for atmospheric analysis. With this powerful instrument, scientists can detect the faintest traces of molecules like water vapor, methane, and even signs of biological activity. This ability to study exoplanetary atmospheres is not just an academic pursuit. It is a journey toward understanding the delicate balance of conditions that allow life to flourish. As we analyze the atmospheric compositions of these distant worlds, we learn not only about their possibilities for life, but also about our own environment and the challenges it faces in a changing climate. In many ways, this research reflects back on Earth, prompting us to appreciate the intricate, fragile systems sustaining life on our own planet. By understanding the diverse atmospheric phenomena present on exoplanets, we can draw comparisons that enhance our comprehension of everything from weather patterns to climate change here at home. Every discovery adds a thread to the vast tapestry of knowledge that we as a species continuously weave. As we marvel at gases swirling through the atmospheres of distant exoplanets, we are reminded of the interconnectedness of the cosmos. Whether a planet has a thick, hazy atmosphere or a thin veil of gas, each gives us clues about its history, its evolution, and perhaps its potential for supporting life. The knowledge we gain extends beyond scientific calculation. It evokes a sense of wonder and responsibility toward our own world. It makes us acutely aware of the stakes involved as we navigate our own environmental challenges. Beyond the scientific pursuit, let's not forget that each discovery brings with it the potential for new stories, new myths, and new connections to the universe. The human spirit is deeply tied to its quest for knowledge. The act of searching for life on other planets gives us a deeper appreciation for the life bursting forth on our own. It awakens within us a profound sense of humility, inviting us to reflect on how we care for our home and each other. This journey into the unknown is ongoing. With each advancement in technology and each new discovery, we are reminded that the universe is vast and full of mysteries yet to be solved. The quest to understand our cosmic neighbors is intertwined with our journey towards self-awareness and understanding. The pursuit of knowledge often leads us back to the essential questions. Who are we? Where do we come from? And perhaps most importantly, what does it mean to be alive in this profound universe? As we conclude this segment, let's take one last moment to gaze up at the night sky. Each point of light is not just a star, but also a beacon, a reminder of the potential that exists beyond our reach. The findings about exoplanet atmospheres invite us to keep our curiosity alive, to dream of what lies beyond, while cherishing the beauty and complexity of the world we inhabit. If you found this journey through the universe captivating, we invite you to share in the exploration further. Follow our channel and like this video to stay connected as we continue to unravel the wonders of the cosmos together. Remember, in this vast universe, every grain of knowledge brings us closer to understanding the extraordinary narrative of life itself. Thank you for traveling with us through the stars.